Hi, everyone. Thanks for joining us. I'm excited because this is going to be a great one today. Today, we're going to be talking about how to design for laser plastic welding. My name is Jason Dornbos. I am the Marketing Communications Manager at Extol, and presenting today will be Drew Jelgerheis. He is our laser welding specialist. And we also have Ben Lotschutz, or however you pronounce his last name. He is also a laser welding expert. He does a lot of hands-on work in our process development center. And then we have Nick Flesher, who is our Director of Engineering and our laser welding business unit manager. So before we get going, I want to quick point out that there is a question and answer feature in this webinar, and you can go over to your right-hand side of your screen and you can put in your name and you can type a question or a comment. Why don't everybody who is on go there and just say where you're joining us from today, and that way we know it's working and everybody has access to it. If you don't see the panel over there, you can look up near the top, and there is a little question mark box that looks kind of like a chat window. You can tap that and open up your question panel and ask a question. So with that, we will get started. Drew, take it away.
All right, Jason, thanks for that great introduction. And yeah, we do look forward to your questions. Welcome to our second live laser plastic welding webinar. And thanks so much for joining us. In our initial webinar, we focused on how to get started with laser plastic welding. We had a great turnout and a long list of engaging questions. If you haven't had a chance to see that webinar, we will provide a link for that recording at the end of this presentation. We also created an FAQ from the Q&A period that we cut to the chase of many of your questions and our answers. We'll provide a link to the FAQ at the end as well. Today, we'll be taking a deeper look at guidelines for designing products for laser plastic welding. It is our goal to provide the necessary guidelines to equip designers and engineers with the knowledge they require during the concept and design phase of their products. As a quick overview, we plan to cover the following items. The laser plastic welding process, just as a quick review. Then the laser plastic welding joint designs that are covered in our design guidelines. And then a couple of examples converting some joint designs from other processes. And finally, just a quick reminder about optimizing laser plastic welding equipment and how Extol approaches that from a value standpoint. We got a great diversity of participants ranging from OEM automotive to several tier and electronic suppliers, some life science OEMs, and several product design organizations signed up. We look forward to an equal diversity of questions and applications. We plan to work through the following agenda in a quick 20 to 30 minute presentation covering the basic topics, and we look forward to answering questions at the end of the presentation. Okay, so let's do a quick review of the laser plastic welding process. The three steps are clamp, heat, and hold. A clamping tool presses together the parts to be joined. The laser beam penetrates through the transmissive component with some energy loss and melts the surface of the absorbing material, shown in black in the image. Heat transfers via conduction to plasticize the adjacent surface of the upper transmissive material. This process is precisely controlled and continuously monitored during laser welding to ensure a repeatable quality weld. After resolidification, the two parts at the joint have been reliably and cohesively bonded. A properly designed weld joint can result in a near parent material weld strength. The three key elements that we see for getting a successful laser weld are the following: intimate contact, IR transmissivity and absorptivity of the material, and the compatibility of those materials. As we described in the last slide, energy from the lower absorptive component conducts to the upper component. To ensure proper heat conduction, there must be intimate contact during welding. The next two key elements are material specific. Transmissivity and absorptivity of the upper and lower layers, respectively, allows for the true transmission laser welding to occur. Transmissive is not the same as transparent. Transmissive materials can appear almost opaque to the eye. On the flip side, most absorptive layers will be opaque. However, absorbing materials are available that can make clear plastics absorb the laser wavelength. Material compatibility is directly related to weld strength. Like materials will provide the best opportunity for maximum weld strength. Plastics with similar properties such as chemical makeup of the polymer chains, as well as the melt temperature and melt flow, can also be bonded using laser plastic welding. In future webinars, we can go deeper into some of the material factors such as melt temp overlap, reflection, absorption, transmission, scattering, and refraction. All things that go into successful laser welding. We'll share a material compatibility chart later in this presentation. Designers should take note of several important items to consider based on these key elements. Surface contact, including flatness and any potential blemishes. Width of the weld rib. Thickness of upper transmissive material. Support for the weld rib, both top and bottom. Material is another key to this process, and Extol has experience and partners in the plastic material world, so we can be an extension of your design team. Here's a link to our design guidelines. You can go to our website and get a download, or type in this case-sensitive direct link and download your own PDF for your files. This set of design guidelines is what we're going to cover in depth coming up. The three main types of welding joints are lap, T, and radial. We'll cover those in order. So the first one, a simple lap joint. Lap joints are the simplest of designs. Very often they are the entire part on a single plane. As described, the parts that utilize this type of joint overlap each other partially or completely. Typical applications include microfluidics, screens, or textile embedding. Due to the typically large weld area, the weld collapse is smaller than a T-joint, which will be covered later. We are currently working on an application welding an extruded tube to a thermoform tray with a simple lap joint. Another application we're working with utilizing this type of joint is welding a film to an injection molded base for a medical test application. So as noted here, plan for 0.1 to 0.2 millimeter collapse. That's not a lot, but because of the large surface area, that's fairly typical. And as I mentioned, microfluidics, films, screens, and textile embedding are some of the applications that's used on. Another lap joint would be the inline. And this might be used for something where you're trying to have a flush surface, or maybe something that's inset. And so here, again, the 0.1 to 0.2 millimeter collapse is typical. And you will get no weld flash protruding using a joint like this. Side by side here, we've got three common lap joints. Sacrificial rib joint, which we didn't cover earlier, allows for more weld collapse. The addition of this rib can also accommodate molded part variation, more molded part variation. So with that, let's jump to T-joints. T-joints are used on parts that, when assembled, have a joint that is typically perpendicular to the mating surface, thus creating a T shape. The T-joint is similar to weld joints you might see on vibration welding with that protruding collapse rib. Many ultrasonically welded parts use T-joints as well. Although the weld rib looks different, it's still a T-joint. They both can be converted to laser welding relatively easy. There's typically more weld collapse when welding these joints, and this provides for stronger welds because of a larger heat affected zone. Collapse ranges vary from 0.2 millimeters to 0.5 millimeters, and we've shown an example of a welded part next to the image, just kind of help you understand the final welded image and the flash that is quite minimal on both inside and outside of the welded part. The lower skirt T-joint, again, similar collapse. The skirt acts here as a flash trap. You could also use sub-flush assembly here. So as the part collapses in, you can get the upper transmissive part to be sub-flush to the lower component. The beam spot, as shown in the image, is the exact width of the joint. In reality, we tend to focus the beam spot such that it's slightly larger than the joint. This allows for any variation there might be in parts. And in this joint design, the larger beam spot allows for the ability to have some softening of the adjacent material to the welded interface. Upper skirt T-joint, the overlap can accommodate hiding the joint as well as location feature for upper to lower. The part itself does not have designed-in collapse control. Collapse control, however, is a robust process monitoring technique used to ensure good weld quality. We control this with a precision depth instrument for closed loop processing. This can be utilized for pre-weld alignment and even allows for a flash trap. Next T-joint is the upper skirt sacrificial rib joint. This design allows for flash trap and flush part design. The collapse rib helps overcome part variation and closed loop feedback of weld position. Each application requires its own unique collapse distance. The next T-joint is the straight sacrificial rib. Image on the right shows a post weld with the minimal flash on inside and outside of the component. This is a simpler design that could allow for a flat stock upper component. Sacrificial ribs should be designed with a greater height than anticipated part tolerance. T-joints side by side. Here are the 5 typical T-joint samples. In every case, the lower component collapses during weld and flash is generated. The various designs allow for components that are very simple to more complicated for hiding the flash or creating a locating feature. Now let's jump over to radial welding joints. Welding a circular assembly can be accomplished using laser welding. As shown here, you need to design in part interference. Plan for 0.1 to 0.4% of the part diameter per side for interference. The angle of interference depends on overall part geometry, aesthetics, and strength, and that angle should be between 45 and 85 degrees. Radial welding requires interference to get intimate contact. We described that in the key elements, and so getting that intimate contact requires the interference. And using that guideline of 0.1 to 0.4%, an example would be a part diameter of 5 inches. 0.1% would be 5/1000ths of an inch interference per side. 0.4% then would be 20/1000ths interference per side. Tooling can allow for radial welding without moving the part during welding. By using ray trace software, we can engineer the angle and position of a mirror tool to reflect the laser beam from an upper scanner to a right angle entry as shown in the image. Extol has worked with several customers, providing design feedback for conversion of glued and spin welded joints using this weld joint design. By replacing these assembly methods, the part is cleaner, stronger, more aesthetically pleasing, and better quality final assembly. Now we're going to jump into some of the examples we described as the next phase, and that is conversion of parts from one welding process to the laser weld process. And Nick Flesher is going to lead us through this.
Great, thanks, Drew. We'll just get into a couple specific examples. Vibration welding to laser welding is something that we do commonly see. As you may know if you're on this webinar, laser welding can provide a substantially cleaner weld joint. And so that's the key reason we see customers come to us for a conversion of vibration welding to laser welding. Every weld technology has its strengths and ways that could be better. So we'll just kind of talk around a couple, one specific application that we've seen. But the reason mainly is elimination of particulate. We do see as a byproduct of transitioning from vibration welding to laser welding that you can have material reduction, and that comes in the form of the return flange that may not be necessary, and in some collapse, as you can kind of see as illustrated by the graphics to the left, the collapse of laser welding with comparable strengths in many cases is less, so you may need less weld rip height. And in some cases, I say, laser welded parts can be just as strong as vibration parts, and without a design change in some cases. So, Drew, if you could advance to the next slide.
Absolutely.
What we'll see here is a couple images. For confidentiality's sake, we've got some very close up, and we'll speak in generalities, but you can see a typical vibration weld. This is a glass-filled nylon application on the left, where you see a variety of different kinds of flash. You can see angel hair, dust, inconsistencies in vibration welding, and a similar material and application on the right, where we did a laser welding application. You can see a much smoother, to some degree more uniform flash, and actually substantially less. These two images don't quite show them scale to scale, but this is a very common situation with difficult to weld materials, glass-filled nylons, PBT. In some cases, there's a couple key relationships we formed with some material suppliers that have optimized PBT, and then PC, ABS, which can be kind of stickier for hot plate. Vibe welds quite well, but can have some challenges with particulate. Those also can be converted successfully in many cases with laser welding. Strength, as we've talked about, and then around this particular application, just to kind of say what you might expect if you convert from a vibration weld to laser plastic welding. We saw in a case study where internal cleanliness showed a complete elimination of particulate, where we had that particular application was an underhood component, and it had unacceptable internal particulate. So definitely feasible. In this particular case study, we proved feasibility and cleanliness without any design changes. So just keep that in mind. Typically, we see that we need 2.5 millimeters or so of transmissive thickness. So yeah, if you've got that sort of application, we'd love to take a look and see if it's feasible. You may not need changes to your part. In some cases, there are changes required, but we definitely can identify those in our applications lab. For spin welding, very similarly to vibration welding, we've seen a handful of applications come through with that desire to eliminate particulate, and actually in some cases eliminate flash traps and provide opportunity to remove return flanges. So there again, there's some some material elimination that can be required, minimizing that material, that excess material. As Drew kind of mentioned, the parts are pressed together, and then the laser is applied radially, typically by mirror. In some cases, there might be other methodologies, but the interference that you can kind of see based on these graphics show a tongue and groove joint that was converted to a angle joint where we provided that intimate contact by the part design themselves and proper tool design and press design.
Great. Thanks, Nick.
Yep.
As we mentioned earlier, material compatibility is one of the keys to a successful laser plastic weld. And this chart, which was compiled by Dr. Klein, covers many of the most widely used thermoplastics. This can help when you have a situation where you need to have a different material in the lower than the upper. And this allows for at least an initial understanding of the weld quality when combining two different materials. And so let us help you with that. We can provide this information. You can ask us, we can dig into it. But at the end of the day, really, testing is best. And so we can also offer that as well. And of course, the other thing to remember is that transmissivity and absorptivity rules apply when you're doing different materials as well. From a market standpoint of where you can buy and get work with companies getting laser plastic welding equipment and tooling, there's really a continuum from commodity to solution. And we like to show this because although there's many different ways to achieve what you need from an equipment and tooling standpoint, we believe that Extol provides the full turnkey configurable laser welding solution, which takes into account all the necessary items. There's a lot of great integrators out there. We work with them as well. They're not 100% familiar with the welding process and the material science that goes into it. We can work with them, create a great solution. We also work with laser component manufacturers. Again, very good in their own expertise field, but they're often using laser for many other things than just laser plastic welding, for instance, cutting, marking, and metal work. And then there's the standard plastic joining equipment builders. Again, pretty astute with many of the things that we're talking about here, but tend to want to put your product into one of 3 or 4 or 5 boxes. And so we think that the best solution is when we look at your application and configure the solution to best match everything that you need to provide the best manufacturing solution. And when, we're talking to designers here primarily, when working with Extol, we can provide part, process, and equipment solutions from the very beginning of your concept and design process. So then we kind of get to that Venn diagram, and Extol sits right in the middle there. We believe that that's really important to getting the right welding solution. And notice I didn't even say right laser welding solution, because Extol also offers many other types of welding plastic solutions. And so we get the application, we're going to work with it and try to find the best for you. A PDC, from a designer standpoint, we can help with specific part design suggestions that will optimize the strength and look of your parts, along with providing input that will increase the robustness of your process. Many times you just need more risk mitigation and empirical testing to prove your point. So we've got a lab welder where we can do testing, trials, samples, and prototype welding. Let us be your material experts. As you continue to navigate the daily grind of design challenges, we can step in, work with your material providers or our partners, and help with blends and different material optimizations that'll be best for your application. And lastly, many teams are cross-functional, and so If we're engaging with you, we can engage with your manufacturing and process engineers as well up front. And our team is very astute at DFA, DFMEA, and risk mitigation. All things that we want to leverage early on in your design project. So in plastic welding with Extol, Extol's team of experienced engineers is ready to work with your team from concept on into production. If you're wondering if laser is right for your design requirements, engage our team of experienced experts to help you get the right welding solution. Some of the benefits Ben mentioned, or Nick mentioned a few, and I'll just review them briefly. No particulate, very, very clean process. The flash is minimal compared to many other processes. The precision application of the energy is unparalleled. The equipment is very flexible in terms of process setup, tool changes, and product changes. The miniaturization of parts that need to be welded is very, very, very successful with laser welding because of that precision application of the energy. And it's also safe for sensitive parts, say perhaps printed circuit boards or lower temperature materials in adjacent situations. To best serve you in the concept phase, we want as much information about your application as possible, including material types, colors, additives, fillings, the CAD or other drawings, what your function of your part is, and the requirements that go along with that. Things like weld strength, hermeticity. Cycle time is important to understand how best to approach it. What's your annual volume? And then the project timeline, of course. So to best leverage your design and work with us, the earlier the better. You know, it's been said that over 70% of the cost is established early on in the concept and design phase. And so the earlier you can engage and we can get this information and provide solutions, the better off it's going to be for all of you. With that, we just want to say thank you for joining us. Here's the links. We've got a link to our laser welding page, a link to our intro to laser welding webinar, and a link to our frequently asked questions regarding laser welding. We look forward to working with you on questions coming up. Let's let them rip.
Thanks, Drew. So yeah, there were a few questions that came in during the presentation. I'll just get started with those right now. So the first question, can a butt joint between two absorptive materials be achieved? For example, two highly glass-filled polycarbonate parts.
Hey, Jason, I'll go ahead and field that one if that's okay. Everyone, this is Nick. Yeah, that is a situation that sounds like it could be a bit of a trickier application, but still potentially feasible. Two absorptive materials where transmissivity isn't as favorable as it might be otherwise, can still be achieved. Optically, as Drew pointed out, optically and IR transmissive are not the same thing. We have done some glass-filled nylons, as I mentioned in the case study. This question actually came in before that. And a natural can actually be welded very robustly. So I would say that sounds quite specific around an application. We'd love to, as Drew said, take a look, even try it in our lab. Welder, we do feasibility trials with material, many times complementary. So it all depends on thickness, depends on the weld geometry, depends on the material, and if there's any differences between the two, which in some cases we'll work with customers to have the correct, it's an additor that could be molded in or added on top of the part as a different operation. So the answer to the question is yes, with the caveat of it depends.
Thank you. Another question here. What percentage of the material can have glass filler? This person has polypropylene material.
Yeah, typically we see, we request 20% on average, but we've done those higher glass contents, again, based on weld joint thickness. So we can weld with glass filler, and to say specifically what the limit is depends on thickness heavily and what resins might be molded in with it, but usually 20 to 30%.
Great. Another application question. Assuming that the clamping can be achieved, can we weld with laser around a deep counter bore? This person's trying to replace screws with a deep counter bore, and then the laser would weld around the ring where the bolt head normally applies pressure.
Yeah, I love this question. That tells me we've got the right folks on the call here. Basically, as a general rule of thumb, if you can get a clean line of sight for the laser beam, since it's through transmission in this particular webinar, if you've got a clean line of sight without shadows, and even sometimes without, we can do some tricky things with tooling to reflect the laser beam. As this person describes that question, I would say it seems feasible. As long as pressure can be applied, you've got the right materials, and you've got a good line of sight, and even then, with some shadowing, as we call it, we can bend the laser around any parts that might be in that line of sight. So,
awesome. Another question here is, I have a very small device. How small can I make my weld rib?
Great question. As small as possible. In some cases, as Drew kind of showed, there may not even be a weld rib. So, especially for small devices, miniaturization is a great way to join those parts is with laser plastic welding. So, we've seen no weld joints up, and very small, 0.5 millimeter, 0.2 millimeters. So, absolutely, small as you can get them. Laser should work.
Great.
Just to add on to that, Nick, typically if it's smaller than 0.7 millimeters, that's going to require a mask, because the beam spot can't typically get smaller than that, and we can work with you on that as well.
Well, that's all the questions that we have. If there are more questions that people think of after the event, feel free to follow up with Drew. Otherwise, you will receive an email soon, later this afternoon, with a recording of this event, as well as PDF of the slides that were used. Thank you, everybody, for joining us today, and have a great afternoon.